Good morning. I'm Ziqiang from Fujitsu. Today I present Scalpel, a training-free method that mitigates multimodal hallucination in vision language models through fine-grained alignment of tension activation manifolds. This is joint work with Ru Jianliu, Sansan Yu, Satoshi Nakata, and Koichi Shirahata. I will first outline the problem and limitations of existing approach, then introduce Scalpel's three-stage framework, highlight our key innovations, and conclude with strong experiment validation. Larger vision language models often generate plausible but factually inconsistent outputs. For example, answering zebra when only houses appear, or hallucination objects not present. These errors stem from two root causes: strong language plows inherited from pre-training and crucially misaligned cross-model attention where models over-attention to relevant visual tokens. The stakes are high. In healthcare, autonomous driving or security systems, such hallucination can cause critical failures. The core challenge we address is how can we correct attention patterns without retraining the model, or introducing multi-step decoding latency. Existing method for short here. Training-based approach like MIA, DPO, or DAMA require expensive retraining with high-quality feedback. In practical for deployment, training-free post-processing method like VCD or Opera apply coarse-grained corrections using fixed directions and often require multi-step decoding, adding latency. Critically, they lack token-level granularity. They can't adapt intervention per attention pair or per generated token. This creates key gap. Fine-grained dynamic attention correction that preserve vision memory alignment while suppressing hallucination. Scalpel bridges this gap through a three-stage inference-time pipeline, no retraining, single forward path. First, we model attention activation distribution as manifolds. Gaussian Mixture Model capture multimodal patterns or trusted activation, those producing correct answer and hallucination-prone activation from perturbed images. Second, we compute an optimal transport mapping between these manifolds using the Schrödinger bridge formulation. This yields a minimal energy control place at smoothly transport activation from hallucination-prone regions toward trusted regions without excessive perturbation that would break vision language alignment. Third, during inference, we apply dynamic token-level intervention. For each generated token, we identify its component membership in the hallucination-prone GMM, retrieve its trusted counterpart, and apply a confidence-scaled correction vector only to a top key. Critical attention has identified via logistical regression problems. Scalpel has the key advantages of training-free plug-and-apply correction with token-level granularity and preserves models' linguistic knowledge while suppressing visual hallucinations. Why we use GMMs? Single Gaussian oversimplified activation distribution. GMMs capture a multi-peak structures critical because different attention heads contribute differently to hallucinations. We train separate GMMs over on 1,500 trusted and 1,500 hallucination-prone samples per head. The Schrödinger bridge of information entropic optimal transport as a stochastic control problem. For GMMs, we solve a linear program to obtain optimal transport weights lambda star between components. This gives us a closed-form mixture policy that for any activation computes the minimal activation direction towards its trusted counterpart. Crucially, our dynamic intervention scale corrections stressed by component convenience, high convenience hallucinations receive strong correction, and we intervene only on top key heads per layer, minimizing computation overhead while maximizing impact. We evaluate on POP, measuring object hallucination via binary queries, and MME covering 14 perception and recognition subtasks. Baselines include vanilla baselines, VCD, Opera, and ICT. We tested on LLaVA 1.57b and Q1 2.5BL 7 billion, and with GMMs of 32 components and alpha base equals 1.7, 1.8. On POP with LLaVA, a Scalpel achieves 85% accuracy on Coco adversary, 7.6% over vanilla, and 2.4% over ICT. The prior best gains are largest in adversary settings, 10.87% of F1 on Coco adversary. Critically, we show strict dominance or no quantum jump across any of the 9 subsets. With Q1, a strong best model, Scalpel still gains 5.1% average accuracy over ICT, peaking at 9.9% on Coco random. Let's confirm strong cross-architectural generalization. On MME, Scalpel lifts LLaVA's total score to 758 and 8.5% over vanilla, with largest gains in counting, positioning, and common sense reasoning. In complex reasoning, we achieve 141 versus ICT's 137, absolute dominance. Application studies confirm 32 GMM components yields optimal granularity. More importantly, image level and object level interventions are complementary. Image level alone gives 7.4 accuracy. Object level alone gives 7.3 improvement, but combined they yield 7.6 improvement, super additive effect. Let's justify our four-line. Qualitative cases show Scalpel element non-existing objects, detecting missed items, and correcting a spatial relationship while preserving accurate reasoning. The model no longer makes redundant assumptions like requires verification when visual evidence is clear. In summary, Scalpel makes 3 key contributions. First, a novel training-free method for fine-grained token-level attention corrections. Second, a theoretically grounded alignment mechanism using GMM and Schrödinger bridge for minimal cost manifold transport. Third, sorter results with strict dominance across bitmaps, 7.6% improved accuracy over vanilla models, and 2.4% over prior best without retraining or multi-step decoding. Scalpel is multi-agnostic, deployable in resource-constrained environments, and opens a new direction, treating hallucination mitigation and manifold alignment rather than ad hoc post-processing. Future work will explore the infinite component GMM limit for continuous correction. Thank you. I welcome your question.